My dear students, welcome back to our video classes. Today, let us discuss the continuation of chapter solution. I hope I can finish the chapter with this video, and tomorrow with another video I will come up with the numericals. Okay, welcome to the class once again. Today I am going to discuss depression in freezing point. You know, depression in freezing point is a colligative property. We already discussed what are colligative properties, what are the different types of colligative properties, etc. etc. Colligative properties are the properties of dilute solutions, and those properties depends upon number of solute particles only, not the nature of solute particles. And we have four different types of colligative properties. They are dip, relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. Okay, we can move on to depression in freezing point. We know what is freezing point. Sometimes we refer freezing point as melting point. Both are same value, same idea, but the name indicates the reference through different directions. Suppose you have a solid that wanted to make liquid, melting. That happens in a temperature that is called a melting point. Or you have a liquid water, you want to make it solid, that's called a freezing point. In the case of ice, which melt to water, that is liquid water, solid liquid, that is ice melt to liquid, that melting point is 0 degree. You have liquid water, you want to make it ice at room temperature, at 1 atm, that is freezing point, that's also 0 degree centigrade. Therefore 0 degree for water is ice to liquid or liquid to ice. Okay, therefore ice to liquid, this is melting point, liquid to water, this is freezing point. Therefore 0 degree is freezing point as well as melting point. Okay, now freezing point or melting point is not colligative properties. The colligative property is depression in freezing point. Now what is freezing point? There is a question. What is freezing point? Freezing point, it is the temperature. It is the temperature. Let me check video. Yes. It is a temperature at which vapor pressure of liquid phase or solution is equal to vapor pressure of solid. Okay? Therefore, freezing point is a temperature at which vapor pressure of liquid and solid are equal. How it is possible? We can graphically express. Okay. It is a temperature at which both have same vapor pressure. That is, at 0 degree centigrade. At 0 degree centigrade, the liquid, water and ice have same vapor pressure. Therefore, they are in equilibrium. They coexist in equilibrium. Fine. I will tell you, if you keep the temperature 0 degree centigrade, could you convert entire water into solid? No. Suppose you have a glass of water, you have put in the freezer, very nice freezer. You have set the temperature 0 degree centigrade. Would you convert all liquid into what? Ice? No. There will be water and ice coexist. They are in equilibrium. Why they are coexisting? Because solid and liquid have same vapor pressure. But 0 degree is the temperature at which solidification starts. That doesn't mean that all at 0 degree and their water of a system will be converted into solid. If you want to convert entire water into solid form, obviously you have to decrease the temperature further. Okay, you keep this. Freezing point is a temperature at which vapor pressure of liquid is equal to vapor pressure of solid. Okay. Now we need following points. Freezing point is the vapor pressure of liquid is equal to vapor pressure of solid. Second point, vapor pressure of solvent always greater than vapor pressure of solution containing non-volatile solute. Non-volatile solute. At any temperature. Okay. Yes. Now, freezing point of solvent is greater than freezing point of solution containing non-volatile solute. That is, pure water 0 degree centigrade, pure H2O 0 degree centigrade, H2O plus sodium chloride solution, it is freezing point is less than 0 degree centigrade, maybe minus 1 degree centigrade. I just give an example, minus 1 degree centigrade. This is called the depression in freezing point. This called the depression in freezing point. Therefore, delta Tf, that is depression in freezing point. What is that? Delta Tf is equal to Tf dash minus Tf. What is Tf dash? Tf dash is called the freezing point of solution. Tf is equal to freezing point of pure solvent. This is always greater than this, therefore negative value will be there. That negative sign has no meaning here. Don't worry about it. You just neglect that negative sign. We are focusing only on what we will call this magnitude. Normally, if you take the water, it will be less negative. This will be like that, minus 1. Suppose it is minus 1, minus of 0, like that. Therefore, it is value is minus 1. Therefore, you neglect this minus 1. Therefore, your value is 1. Depression in freezing point. Yes. Now we can graphically express this. Students, please see how I draw this in graphically. Suppose you have a x and y axis. This is temperature. This is vapor pressure. Okay. Suppose I draw a graph like this. Okay. What is this? Temperature increases, vapor pressure increases. That is the case for every state, whether it is solid, liquid. When temperature increases, vapor pressure. I draw this is vapor pressure of pure solvent. Pure solvent in solid state. This is this graph. Suppose this blue graph represents vapor pressure curve for solid solvent. It increases. Suppose it starts this point starts melting. Okay. Now from there onwards, when temperature increases, that become liquid. Liquid. For the in the case of liquid also, vapor pressure increases. Vapor pressure increases. We can draw like this. Little flattened like this. Okay. This is what I'm doing. This is called a freezing point. TF, freezing point of pure solvent. From that onwards, vapor pressure again increases when temperature increases, but it is just like this. You know why? Because this is liquid, pure liquid solvent. Therefore, the graph will have a different type. Yes. Now, suppose this solvent prepare a solution that is H2O plus sodium chloride. In the case of a solution, its vapor pressure will be always less than that of temperature, that of pure solvent. When you compare to pure solvent, its graph is always less than. It is always less than. Now, suppose it meet here, but very careful. When a salt solution, sodium chloride solution of water, freezes, you will get an ice. Does that ice contain sodium chloride? Do you get my question? You have a salt solution, you freeze it, you got the ice. Does that ice contain salt? That were the part of solution. Never. Sodium chloride will not be there. You taste it. You do the experiment today itself. Take a cup of very tasty, concentrated salt solution, then put in your freezer, refrigerator freezer, then make it ice. Then you ice cube. Then you taste that cube, whether it is salty or not. I tell you, it is not salty, because that sodium chloride will not be the part of solid solvent. Okay, therefore you from here onwards, this is the solution, this is a liquid solution. It meets here. Why it meets here? Because this is the vapor pressure curve of solid water, ice. Vapor pressure curve of solid water. You have no separate salt solution solid. That's not possible. If you freeze the salt solution, only water will become ice. Only water becomes the solid. That point is meeting here. Therefore, solution starts to freeze here. This is the temperature curve, Tf dash. That is, Tf dash is less than Tf. If it is 0 degrees centigrade, or suppose it is 273 Kelvin, I will tell this is 269 Kelvin. In Kelvin. If it is 0 degrees centigrade, it will be minus 4 degrees centigrade. Therefore, this is the solution. This is the vapor pressure curve of the solution. That solution curve meets pure solid solvent curve only at this temperature. And this is the point where the solution and pure solvent or ice have same vapor pressure. Therefore, this is the freezing point of that solution. And this is the delta Tf. Delta Tf. As usual, delta Tf is equal to Kf into Em. Delta Tf is equal to Kf into Wb, Mp, Wa into 1000. What is Kf? That is called the cryoscopic constant. here cryoscopic constant or molal depression constant. Molal depression constant. Molal depression constant. Okay? Yes. Same equation in the case of elevation in boiling point. Molal depression constant. Now, in summary, a water will become, a solvent will become freeze at lower temperature if you dissolve something there. Okay, I will tell you some example. In the cold countries, there will be very low temperature and there is a chance of freezing of petrol in the vehicle fuel tank. There is a chance. Because if you take petrol only, it's a pure solvent. Therefore, in those countries, they will mix petrol with some other components, such as ethylene glycol, so that you will get a solution. That solution, petrol solution, still is fuel, not harmful for our vehicle, not affect our mileage and anything else. Therefore, they will use it. They use the solution. Similarly, in Kashmir or somewhere, the places such like, where in cold period, cold season, in cold season, there will be huge snowfall on the road. Huge snowfall. Therefore, to clear the road, they will spread some salt like sugar, or sodium chloride or something like that, so that snow and salt will form immediately solution. That solution has lower freezing point. Therefore, they start to melting or forming a solution. Okay, because that temperature may not be at a good temperature may not be a freezing temperature. The temperature in that Kashmir at that time may not be the freezing temperature for snow. Solution. Therefore, snow start to melt. Automatically, road will be cleared. Okay, that's all. The points about the depression in freezing point. Okay, students, let us go to next colligative properties, that is osmotic pressure. Osmotic pressure. Osmotic pressure. Why? We have so far we have discussed vapor pressure. Vapor pressure is something different idea, where is the pressure upon a solution produced by vapors of the solvent, or pressure upon any liquid solvent produced by vapors of that liquid. Osmotic pressure is a different idea. Here, before going to osmotic pressure, you have to learn what is osmosis. You learned this in biology. Okay, osmosis. Osmosis is quite natural phenomena. It happens in our daily life. Okay, osmosis happens through membrane. A membrane. Suppose you have a very dilute solution here, or a pure solvent. Okay, take a pure solvent here. Yes, and a concentrated solution here, and this is suppose a membrane. Membrane means skin is the best suitable membrane. This is called semi-permeable membrane. Skin. You know, from here, solvent will move from here. This is called osmosis. Solvent will move from dilute solution or from pure solvent part to the concentrated solution. to the concentrated solution. That is called osmosis. In botany, you learn that solvent is moving from higher potential to lower potential. That's also correct. Higher potential means higher amount of water. Solvent is moving from a region of higher potential. What is the meaning of higher potential? The region where higher amount of water is present, to the lower potential, that is to the region of lower amount of water. That's correct. Dilute solution means solvent is more, solute is less. That is why we call it is dilute solution. Concentrated solution means solute is more or solvent is less. Therefore, solvent is moving from here to here. Yes. Now, that is all osmotic pressure. Now we are going to discuss what is osmotic pressure. Now, suppose this is a case. Suppose I am going to apply a pressure here. Suppose these two are two balloon-like, pressable. Two balloon-like compartment. Imagine two balloon-like. These are two balloon. These two balloon part is separated by a semi-permeable membrane. That's possible. You have a tube. Suppose you have a cycle tube or car tube or lorry tube. One part you cut that two tubes, then join with a semi-permeable. Fit a semi-permeable membrane here. That's possible. Yes. Now this side of the tube is dilute solution. This side of the tube is concentrated solution. Solvent starting moving from here to here. Okay. Now I press this side. Concentrated solution part of the tube is compressed. So that there will be a pressure increased. Because of that pressure, suppose there is a lot of water, solvent is moving. Because of that pressure, the movement of water is decreased. Now, imagine just stops. No movement of water because of that pressure. That pressure is called osmotic pressure. What is osmotic pressure? It is the pressure applied along the concentrated solution side, to stop osmosis. Okay, it is the pressure applied along the concentrated solution side to stop osmosis. Okay, now I apply a pressure greater than osmotic pressure. What is osmotic pressure? Osmotic pressure? Pressure required to stop the osmosis. No flow now. Now I further compress. I keep on compressing. Osmosis decrease. At particular this pressure, osmosis stops. I further compressed. You know what happens? Concentrated solution means there is solvent present. That solvent started to move towards this region. This is called reverse osmosis. Reverse osmosis. What is reverse osmosis? It is the movement of solvent from higher concentration region to lower concentration region when a pressure greater than osmotic pressure is applied. When a pressure greater than osmotic pressure is applied. Yes, this is called reverse osmosis. Reverse osmosis has best application in water purifier. My dear students, you have seen a lot of water purifiers in your school, in offices, in shops, even your house. You check your water purifier and there will be some the company name, prices, and the features, etc. You read that informations given the water purifier machine, you will see that there is RO machine. RO machine. What is RO machine? Reverse osmosis. Water purifier widely uses reverse osmosis. Where pressure is applied in terms of electrical pressure. Okay, electrical pressure, they give that. And there is a semi-permeable membrane also. And what happened, therefore suppose our in water purifier, our tank, you are connected to tank water. You will see that, you will say that our tank water is pure, but still it is a solution. A lot of things are dissolved. When it comes into the machine, when there is a machine part through which there is a semi-permeable membrane, when the water moves that, due to the electrical power, there will be a high pressure is given to that water, and because of the high pressure, only pure water passes through the semi-permeable membrane that will be connected in the pipe. Okay, therefore it is widely used in water purifier. You just check it. Okay, now what is the equation for determining osmotic pressure? Osmotic pressure is also a colligative property, that is pi directly proportional to concentration of the solution, or pi directly proportional to number of moles of solute divided by volume of the solution. Colligative property is a property which depends upon number of solute particle or number of moles of solute particle. Look at it here. Therefore, this is equation, or pi is equal to CRT, or pi is equal to WBRT by V, or WBRT by MB, that is the number of moles into V. This is equation for calculating osmotic pressure. Now, what is isotonic solution? Isotonic solution having same osmotic pressure. Solution having same osmotic pressure. Okay. Hypertonic solution. What is that? It is nothing but a solution having higher osmotic pressure. Having same osmotic pressure and having higher osmotic. Hypertonic. Then hypotonic. Another one, hypotonic, that is lower osmotic pressure. Therefore, same osmotic pressure, higher osmotic pressure, and lower osmotic pressure. Okay. Now, I am going to another very important topic. Very important topic. With this topic, theory part of the chapter is over. That is Vanthauff factor. Vanthauff factor I. Vanthauff factor I. Okay. I want to check the recording. There are many occasions where I will take the classes and maybe mobile is out of focus. Therefore, I have to repeat it again. That happened many times. That is why periodically I check whether is recording correct or not. Okay, let us go to this Vanthauff factor I. Vanthauff factor means, before that, once again you can discuss the colligative property. Colligative property is a property depends upon number of solute particles. Number only. That's a problem. Number only. imagine I take 1 liter H2. To that I added 100 sodium chloride. Added. Okay. And then I calculate a colligative property for 100 sodium chloride because I added only 100 sodium chloride. I added 100 sodium chloride and I got a colligative property that I calculated by mind for 100 sodium chloride. What is colligative property? Property depends upon number of particles. How many sodium chloride I added? Only 100. Okay? Yes. But you know, after reaching in the water, 1 liter water, this sodium chloride, what happened to the sodium chloride? The sodium chloride completely dissociated into 100 Na plus N, 100 Cl minus in the water. In my spoon, I have only 100 sodium chloride, but after reaching water, scenario entirely changed, totally changed. They dissociated, and there is 100 sodium ion, 100 chloride. For water now there are 200 solutes. Okay, it's not sodium chloride. For water there are 200 particles. Therefore, the actual colligative property, okay, is for 200 particles. Therefore, the value I got here, Cp, and the value I got is here, the actual value Cp dash or actual or Cp actual, this is calculated, are different. Which is higher? Cp actual is greater than Cp calculated because only depends upon number of particles. And not only that, Cp actual is equal to 2 times Cp calculated because its number is 2 times greater. It is 100, it is 200. Its number is 2 times greater than this number. Therefore, its colligative property is 2 times of this colligative property. Okay? Yes. This phenomena was observed by vanthauff factor. Therefore, vanthauff, the scientist, suggested that before going to do any calculation of colligative properties, you have to take care what is the vanthauff factor. The vanthauff factor is said that vanthauff factor of this sodium chloride is now, the vanthauff factor of this sodium chloride is now 2. Vanthauff factor of this sodium chloride 2. Why? Because vanthauff factor is equal to total number of particles after association or dissociation. Here dissociation. Similarly, association also happen. I will tell you. Divided by total number of particles before association or dissociation. What is that? After association or dissociation it is 200, before association 100, that is 1. That is 2. Or I said that, or another equation, vanthauff factor I is, I just write, is, another equation he introduced, I is equal to, one is total number of particles after association or dissociation, divided by total number of particles before association or dissociation. I is equal to actual colligative property or calculated colligative property. What was the calculated colligative property? Yes, that is actual colligative property 2 into colligative property calculated divided by colligative property calculated. Or we said that this colligative property actual is 2 times of the colligative property of calculated. Yes, agree? Therefore, these are the Vanthauff factor. This is possible in the association also. I will tell you the association. Association. Yes, suppose you are adding 100 acetic acid or benzoic acid in water, 1 liter water. 100 separately. But you know, that is 100 molecules. Here you know what happens. 2 molecules joined, acetic acid, 2 molecule acetic acid joined like that. You have added separate 100. But after reaching the water, 2 joined. Therefore, you will get how many? Only 50 pairs or benzoic acid, 2 each joined. 50. Therefore, what is the actual number after association? 50. Before association, 100. Therefore, 1 by 2 or 0.5. Therefore, here Vanthauff factor is 0.5. Yes. Therefore, this is all about the Vanthauff factor. Now, let us, for salt it is very simple. We can calculate the value of I. Salt, value of I after complete dissociation. After complete dissociation. Sodium chloride. If it completely dissociated, 2. AlCl3, 4. You got the idea because sodium chloride dissociated as Na plus and Cl minus. This is Al3 plus and 3 Cl minus. Now Al2 SO4 thrice. SO4 thrice. Therefore 2 Al3 plus 3 SO4 2 minus. Total 5. Okay. K2SO4 2K plus SO4 2 minus, that is 3. Now, my dear student, in the case of urea, glucose, sucrose, in this case, no association dissociation, therefore it is 1. Benzoic acid and acetic acid association, therefore 0.5. In this case, association. This is no association dissociation, therefore 1. That is actual and observed are same. Actual and calculated are same. Number of molecule after dissociation or before dissociation are same because there is no association or dissociation. Therefore, our equation for solving the numericals of colligative property should include the Vanthauff factor. Therefore, this is the summary. Students, this is the summary. Each colligative property. First, relative lowering of vapor pressure. That is delta P divided by P0 is equal to I into XP. Depression in freezing point. That is delta TF is equal to I into KF into M. Elevation in boiling point, delta TB is equal to I into KF into M. KB into M. Osmotic pressure, pi is equal to ICRT. Therefore, this equation should be memorized before solving the numericals. And this is the theory part of the chapter. Tomorrow I will solve some numerical based on this equation. Before that, please watch the video completely, get a full idea and come to the numerical class. Okay? I hope you are safe, you are enjoying well the video classes. Have a nice day. Thank you.